Hey y'all, it's good to see you. For those of you coming back from Thailand, welcome home. Today we're going to talk about logistic growth. Logistic growth is one of the most practical topics in calculus. As you may have noticed, when calculus gets concrete, as it did with optimization, related rates, and volume, it also gets complicated. However, logistic growth looks complicated, but is not. Be patient with yourself and get ready for the challenge. A biological population with plenty of resources and with scarce predators tend to grow at a rate that is proportional to the population. This continuous growth rate is represented by dp over dt, which equals rp, where p is the population, t is time, and r is the constant. If you look carefully, you can see the old Algebra 1 formula for a direct variation, y equals kx. However, y is not y here, it's the rate of the growth of the population over the rate of the change in time. Logistic growth is used to do everything from figuring out when a species is going extinct to figuring out how many licenses people can have to kill deer, and all sorts of things like that. So of course we know that most populations are constrained by resources, so even the flu bug is limited and will die out eventually. So instead of being represented by the green curve, which would be exponential growth without limits, the growth curve is actually represented in the blue curve, which is a logistic growth curve. During class today, we're going to be going over the curve as it is represented here in the equation dp over dt equals rp times 1 minus p over k. You're going to see different versions of this. The idea is always the same, and you do not need to memorize this formula. It will absolutely be on the AP exam. It is fairly fascinating how accurate this curve is. As you can see, there is a logistic curve here with superimposed with U.S. Census data through 1940. You can see how incredibly accurate logistic curves are and how useful they are through this simple example.